Okay, so in this lecture, as promised, I want to talk a little bit about a specific type of volume that we're going to calculate. We're going to talk about this type of volume using two different methods. The one that I think is one of my favorites is the disk washer method. It's a very natural name. You'll see that there's a reason we call it disk washer method. And then the other one is cylindrical shells, which will be in a different lecture video. So the disk washer method is basically a method of calculating the volume of a solid of rotation. So what I mean by that is you have f function, and let's just make it a very simple function, like something like this. I talked about this yesterday too, but in the last lecture as well. But so, and you have this, and then you rotate it about the x-axis. You get this, and you want to calculate the volume inside here. So what's the volume inside of this shape? Everything I told you in the last lecture still applies here. So we're still going to partition it between the two values, say a and b. Your function, by the way, is this one, f of x. I'm going to partition it between a and b. It's going to be, this one is going to be your x naught. This one is going to be your xn. And then, of course, this is delta x in between them. And then each of those partitions, if I look at the cross-sectional object, the cross-sectional object for each of those partitions is really just a cylinder. Well, not a cylinder quite, because it has some tilt in it or some function. It's not straight line, and it's not perpendicular to the axis or parallel to the axis. So it's not like this, but we're going to make it like a cylinder. So that's how we get the cylindrical shape in it. So again, cross-sectional area is going to be a circle. It's going to be a circle with a certain radius. And of course, that radius is related to how far it is from the axis of rotation. And that radius, pi r squared, gives you the cross-sectional area. You multiply by delta x, gives you cross-sectional volume, very, very small volume. Then you add them all up from A to B, and you get the pattern. Same thing that we've done in the past. Okay, very good. So I need to first figure out the formula, and your main job here is to find the equation for that radius. That's all. And the equation for the radius in many cases is just f of x anyways, so f of xi anyways. So when I deal with the solids of rotation, which are created by having a function, maybe I draw the picture one more time for you guys, just so you can see. As I draw, you can see what I'm talking about. So you have, again, just a simple function. Try a different color. So you have a simple function like this. This function, if you think about it from A to B, think about it like you create this. Imagine if you would a cardboard cutout for the area below the function above the x-axis, and then you get that cardboard cutout and you rotate it about the x-axis. Now, I don't have to rotate it about x-axis. I could rotate it about y-axis, and that's you can sense the difficulties. I could rotate it about like other lines. I don't want to complicate my shape right now, but I could rotate it about a line down here, a line down there, maybe y-axis, maybe a line here, maybe a line there. So I could rotate about many different lines. We're going to stick to parallel to either x or y-axis, lines that are parallel either to x or y-axis, but still you are going to have many possibilities. So this is a very simple case where I just rotate about the x-axis and my function is a function of x. As I do that, my function, of course, remember that cardboard, that cardboard cutout is going to come and it's going to brush down in the bottom of the shape as well. So that's how you get the three-dimensional solid. And that three-dimensional solid is the volume of that is what you're interested in. It's not a very, like I say, applicable problem, but it's a very nice application of integration and calculating using integrals to calculating volume of an object. So once again, as I was saying, all I need to do is I need to figure out the area of cross sections, and the area has to do with the radius, and the radius is nothing other than f of xi, whatever xi is. So I'm going to have f of xi that represents my radius. I square it, multiplied by pi, that gives me my area, cross-sectional area. Then I multiply by delta x right now, delta x, that gives me my volume of those little pieces. Then I add it all up as I goes from 1 to n, gives me an approximation of total volume. I take limit of it, limit of the Riemann sum. Let's get used to that language again. And that gives me the actual volume. And of course, that become a Riemann integral a to b pi f of x squared dx. That is why we call it the disk method, because the cross sections are always going to be disks. Because remember, you're taking a line and you're rotating, you're getting a shape and you're rotating about the x-axis, you're going to end up with the disks. So for example, you remember the example of the cone example? Let's do that again, but now doing it with this understanding. So I have a line, and suppose this line is y or f of x is equal to say 1/2 x. So suppose this is 10 and this is 5. So the radius of base is 5. Okay, and again, I'm just making it simple. So that's my radius is f of x. So the integral, the volume would be integral from 0 to 10 of pi f of x squared dx. Oh, sorry, actually, you can go further than that. So 250 by 30. Okay, so you can calculate the volume of solid of rotation if your function now is a straight line. So it doesn't have to be a straight line, but that is an example of that. For example, if your function is find the volume of the solid formed by rotating y equal to square root of x over 0 to 4 about the x-axis. Now, although drawing graph is both pleasing and important in solving these problems, so this is what you have. This is 4. Of course, the square root of 4 is 2. So I'm dealing with rotating this object, and I'm going to end up with a shape that looks like this. So although you can try to do your rotational disks and so forth and see what's going on, but you could also just as well integrate from 0 to 4 pi f of x, which in this case is square root of x squared dx. So you can do that. So this is the disk of the disk method. This is the disk of the disk method. Now, if I wanted to do this about a line other than the x-axis, so suppose I do same graph again from 0 to 4, and I rotate it instead of again f of x equal to square root of x, rotated about the line y equal to -1. So suppose I rotate about line equal to y equal to -1. Now y equal to -1 is this line. So when you rotate it, then you're going to actually have something that looks like this. Yes, wider object. So you're going to have to calculate the volume, which you expect a bigger volume, but it's going to be, again, the process is similar. What you have to worry about is the radius again. So you're going to have 0 to 4, no problem. Pi, no problem. But your radius, instead of being root x, this would have been root x. This would have been root x. But your radius actually is longer than that. It's actually 1 unit beyond that because your axis of rotation is y equal to -1. So it's root x minus -1, which is really like we did before, subtracting top minus bottom, but you could also just say root x plus 1 directly if you don't want to do that. So pi r squared dx that's how it works. So that's the case where you look at the moving the line of rotation below the x-axis. So you subtract the function minus the line, whatever it is, which is now becomes plus because it goes below the x-axis. Let me give you another example, but let me now, for the same function, which is probably one of my favorite functions, let me rotate it about, and get ready for this, y equals to 3. Again, f of x equal to root x, same problem. I just changed the rotation axis. Rotate it about y equal to 3. So y equal to 3 would be here. And I was very careful to make sure I will completely above the graph, so I don't have to worry about one side or another side, how they rotate and such. That would just make a messy problem. Now, when you rotate this, let me actually use a different color here. When you rotate this, you get something like this. As you rotate it about y equal to 3. So you see, actually, even the shape that you would get has changed through that rotation. But no problem, we can still calculate the volume. Still is going to be 0 to 4. Still going to be pi something squared. But that thing squared is now 3 minus root x. And now you're like, well, hold on, sir. Why is it 3 minus root x? Well, for every x, this is root x. This is the radius I'm trying to find. The whole thing is 3. So 3 minus root x is r, is the radius. Basically, subtract whatever is above. If your function is above the axis of rotation, then function minus axis. If it is below the axis of rotation, then axis minus function. Now, let me finish this one because I don't know if you guys remember how to integrate these. Not too complicated, but you have to square it. You get 9 minus 6 root x plus x dx. It's a simple power rule for the whole thing. Pi 0 to 4. I'm going to expand it to 9 minus, I'm going to rewrite it. 6x to the 1/2 plus x to the 1 dx, which is pi 9x minus 2 times 6 over 3x to the 3/2. I just use the power rule there, plus 1/2 x squared from 0 to 4. Pi 9x minus 4x to the 3/2 plus 1/2 x squared. So if I plug in 4, I get 36 minus 32 plus 8. Again, making sure I did that correctly. 8 times 4, 32, and 36, and 8. Perfect. So I get 4 plus 8, which is 12 pi. And 0, of course, everything is 0, so no difference. Okay, so that's how you calculate the solid if I'm rotating it about the line above the rotational, about the function, sorry. Okay. Now, let's just see what happens if I rotate it about, say, y-axis. So same function, let's just play with the same function while we can, and then I'm going to add something else to this. So now I'm going to change it so the graph is like this still, but now I'm going to rotate it about the y-axis. The shape I expect to get, and I hope this makes sense, the shape I expect to get is something like this. This part. Oh, sorry. Yeah, it depends again which part you're trying to calculate. But this one is going to be the region I'm going to calculate the volume of. Either it's going to be the question would read, rotating the region bounded by the graph and the x-axis, which would be the one that I've shaded, about the y-axis, or the question is going to read, rotating the part of the graph bounded between the graph and the y-axis, which in that case, it would be this guy. So you're going to get that cone look, funnel looking shape. Let me do the funnel looking shape first, and then I'm going to do the other one. So let me do the green part first. So if I want to calculate the green part, now I have to calculate, instead of integrating in terms of x, now since I'm rotating about the y-axis, I'm going to partition in the y-axis, and the disks are going to be in the y direction. So instead of delta x, I'm going to use delta y. So the integral is going to be 0 to 2, because now I'm going in the y direction. dy pi, and your radius would be a function of y. Now you remember how it was y was equal to square root of x, which means x is equal to y squared. So it'll be y squared squared. So once again, because I'm rotating about the y-axis and using disk method, my bounds would be in terms of y. That's where the 0 and 2 came from. My measure is going to be in the direction of y. I have delta y. And my radius would be a function of y and not a function of x. And that's how I converted from x to y. And that's it. And you just integrate that. That's how you do this. Now, as promised, let's figure out, and this is actually a new part of this presentation, because now we have to figure out what is the color. Actually, I guess they go with that color. Let's figure out what's the area of this part. Okay. So, and this is a new part of the lecture. You have a solid that comes from rotating the outer part of the circle. So let me draw the shape one more time so I can explain it more better with the new picture. So this would have been root x, go get to 4. Yeah, no surprises there, no surprises here. And so it's going to be a region that's bounded from this slope, and then you rotate it about the y-axis, so you get this. Okay, so that's what I want you to expect. But notice what happens. If I want to calculate the shaded region, I have to calculate, if you would agree with that, I have to calculate maybe all of it and take out the inside piece. Now, I'm not telling you to use what you calculated here. That's not what I'm saying. I'm just saying, just think about that logic. You calculate all of it, then take out the inside piece. All of it, the radius would be from here to here, which is 4 units. So it's going to be integral from 0 to 2 of 4 pi 4 squared dy. And then take away integral from 0 to 2 of pi y squared dy. I could rewrite this as a single integral, 0 to 2 of pi 4 squared minus y squared dy. That's why we call it washer method, because each one of these green shaded ones, if I calculate the cross sections, the green shaded one, the cross sections are going to be between circular objects, circular disk, where the inside part of it has been taken out. So if I look at the side view or above view of it, it looks like this, where again, this the green part is here and the red part is here. So that's why it's called the washer method, because you're taking out a hole inside of the washer. Hence the washer method. Anyways, you can calculate this if you wanted to. Another example that I like is something like this, and let's go back to the same disk washer method, but let's make it a little bit more elaborate. So suppose I have find the volume of the solid formed by rotating the region bounded by, let's just do y equal to x cubed and y equal to x about the line x equal to -2. So if I look at the graph, the object x cubed is like this. It does have this part, but I don't care about that portion of it. Let's just say above. Actually, yeah, you're right. Let's put above x-axis, because yeah, the negative part also would be there, but I don't want to play with that. And then this is y equal to x line. This would be the region. I'm rotating about the line x equal to -2. So I'm going to get something like this here. Something like that. Now again, because I'm rotating about something parallel to y-axis, the integral is going to be dy pi. I have to find bounds of y, which I get by setting these two equations equal to each other. So I get x is equal to x cubed, which means x cubed minus x equal to 0, x equal to 0 or x equal to, there's a plus minus 1, but remember we're only looking at the positive one, so x equal to 1. And if x equal to 1, then y would also be 1 for both two functions. So my integral is from 0 to 1. My outer radius, I need outer minus inner. My outer radius is going to be a function of, has to do with y equal to x cubed or x equal to cube root of y. It has to be a function of y. So it's going to be outer radius going to be cube root of y squared. Inner radius has to do with y equal to x or x equal to y, doesn't matter. So it's going to be, oh, sorry, I need to make a correction here. Let's make it, I'm sorry, I have to make a correction for the outer radius. Outer radius, this portion of it is cube root of y. But then you have to also add this missing part because that's how far away it is from the axis of rotation. So it's going to be cube root of y plus 2 or minus -2, doesn't matter, squared. Yes, sorry about that. Plus, and the inner radius, similar pattern, is going to be this portion, which is just y, and then you add 2 to it. And that's how, again, washer is because you're getting those are like washers you have for your screws and so forth. You're getting a hole in the middle of a circle. So like a lifesaver, right? Like a donut, you have a little hole in the middle. So that's why it's called the washer method, disk washer method. So disk washer method are not two different methods. It just depends what shape you're dealing with. If your shape is a solid disk, then it's a disk method. If it has a hole in the middle of it, then it will be washer method. You can play this game with many things. In fact, there is a homework question on which for synchronous classes, I usually assign this problem, but I think it gets a little bit too tedious. Problem number 19 through 30, which draws 3 regions in a square and asks you to rotate it about each of the sides of the squares. So imagine 3 regions, 4 sides, that's about 12 different integrals you would have to write. I passed on that one. So, but if you're interested, you can read those and consider all those possibilities. Okay. So I hope this explanation, I kind of showed you guys how to deal with different situations and different cases. Actually, I'm kind of like, I want to do one more for you guys. Let's do the same one, but let's rotate it about the line, say x equal to 4. Okay, x equal to 4. So I'm going to draw a new shape, of course. But so this is x equal to 1, y equal to x. This is y equal to x cubed, and I'm only looking at the positive side. This is, of course, x equal to 1 would have been, x equal to 2, x equal to 3, and x equal to 4. And this is the line of rotation. And after a while, the process seems very repetitive, but you still have to know what is the region you're calculating volume of. So once again, I do it in terms of y. So 0 to 1 pi. The outer radius, again, you don't look at the rotated version of it. You look at the original shape, okay? So you look at the original shape. The outer radius is this. The inner radius is this. Again, it's going to be washer. So the outer radius is going to be 4 minus y squared. Again, remember, this is y, this is 4, and this will be 4 minus y. The inner radius is not going to be 4 minus cube root of y squared. Again, this is 4, this is cube, this is the radius you're looking for, and this is cube root of y. So 4 minus cube root of y gives you the radius you're looking for. Again, pi r squared, pi r squared. Okay, I hope this helps you to get you through the homework. As I said, I still am going to make a video answering some homework questions too. I'm waiting to see if you guys post any problems you want me to look at, so I won't be just picking my own problems. But yeah, try with this and see how it works. And then once you're solid on this is the last topic you'll see on your test. Once you're solid on this, then we're going to talk about another method of doing this, which is called cylindrical shells. So again, as I said, just practice with this one first, get ready for the test, and then we use cylindrical shells to do the similar idea, but a different method. Which, as I said, I like this washer method a lot, but cylindrical shells also has its own intrigue. So I hope you guys like it. Okay. Thank you, and I'll see you in the next lecture.